please subscribe to support the channel. What if everything we see, every star, every galaxy, even the flow of time itself, exists not in open space, but inside a black hole? It sounds impossible, yet some of the universe's deepest mysteries hint at this mind-bending idea. The vast cosmos we call home might not be the ultimate reality, but the inner workings of a colossal gravitational entity, born from the death of another universe long ago. If that's true, then every black hole we observe could be a doorway, not an end, a gateway to an entirely new universe waiting to be born. The idea that our entire universe might exist inside a black hole is one of the most daring and thought-provoking concepts in modern physics. It challenges not just our understanding of space and time, but the very definition of what a universe even is. In the grand tapestry of cosmology, this theory doesn't just stretch the fabric of imagination, it twists it, folds it, and sends it cascading into realms that border on the philosophical. And yet, for some scientists, it isn't mere fantasy. It's a logical extension of the equations that govern gravity and spacetime, first introduced by Einstein more than a century ago. According to this perspective, the universe we inhabit could be the interior of a massive black hole that formed within another larger cosmos, a parent universe. When that black hole was born, its core, a region of infinite density called the singularity, didn't just crush matter out of existence. Instead, it may have caused a rebound, an explosion of new space and time that became the Big Bang of our own universe. This speculation is not random. It arises from deep puzzles at the heart of cosmology. When scientists trace the expansion of the universe backward in time, everything converges toward a single, infinitely dense point, the so-called singularity of the Big Bang. But the equations of general relativity, the cornerstone of Einstein's theory of gravity, tell us that singularities also exist inside black holes. In both cases, space and time reach a point where known laws break down, and density becomes infinite. The similarity between these two singularities, one at the beginning of our universe and one at the end of matter falling into a black hole, is more than poetic, it's mathematical. This parallel has led some physicists to ask whether they might in fact be two sides of the same coin. If that's true, then the formation of a black hole in one universe could give birth to a new universe inside it. From the outside, that black hole would appear to be a region where everything vanishes, a cosmic sinkhole devouring light and matter. But from the inside, it could appear as a universe in its own right, expanding from a singularity just like ours did 13.8 billion years ago. The event horizon, the invisible boundary surrounding every black hole, might serve as a kind of one-way membrane separating two realms of existence, the parent universe outside and the child universe within. To an observer falling into the black hole, crossing this horizon could mean entering an entirely new cosmos, one governed by its own unique physical laws, constants, and even dimensions. This idea elegantly addresses one of the biggest mysteries in modern physics, the origin of our universe. The standard Big Bang model, while successful in explaining the cosmic microwave background and the expansion of space, doesn't explain why the universe began or what triggered it. The universe inside a black hole hypothesis offers a potential answer. Perhaps the Big Bang wasn't the birth of everything from nothing, but rather a transformation, the continuation of cosmic processes occurring in a larger unseen reality. The collapse of a star into a black hole in that larger universe could have been the seed that blossomed into our own. Such a concept paints a breathtakingly recursive picture of existence. Imagine a cosmic hierarchy in which every black hole spawns a new universe, and within each of those universes, more black holes form, each giving rise to yet more universes, in an endless chain of creation. This multiversal structure would resemble an infinite tree, with each universe as a branch sprouting from the gravitational collapse of another. It's a vision that collapses the boundary between destruction and creation, showing them instead as different phases of the same cosmic cycle. This theory also brings a subtle beauty to the nature of black holes themselves. Traditionally, we've thought of them as the ultimate cosmic monsters, regions where matter is crushed, information is lost, and space and time are ripped apart. But in this view, black holes become the wombs of creation. Their intense gravitational fields don't merely consume, they recycle, reconfigure, and regenerate. The death of one world could be the birth of another. The darkness at the heart of a galaxy could conceal a light so bright it fuels an entirely new reality on the other side. Of course, this is more than just a poetic notion. It finds support in the mathematics of general relativity. When the equations governing black holes are extended beyond their event horizons, they allow for spacetime to continue inward, potentially re-emerging in another expanding region. The interior solution of a black hole's metric, in some models, mirrors the expanding geometry of a new universe. Physicists like Nikodym Poplavsky have explored this idea in depth, suggesting that the Big Bang might have been the white hole counterpart to a black hole in another cosmos. In this sense, the universe inside a black hole could be the ultimate act of cosmic rebirth, a transformation where collapse on one side becomes expansion on the other.
It's a humbling thought. If our universe truly originated from a black hole, then our cosmic ancestry traces back not just to the stars, but to the death throes of an entire universe before ours. Somewhere beyond our comprehension, in a reality we can never access, there might exist a parent cosmos whose own evolution gave rise to the black hole that became our beginning. And perhaps, deep within the black hole scattered throughout our own universe, countless new realities are now forming, each one unaware of the cosmos that birthed it. As speculative as it sounds, this perspective has profound implications for our understanding of space, time, and causality. It forces us to confront the possibility that universes are not isolated, self-contained entities, but connected through a vast network of gravitational bridges. In this view, the multiverse is not a chaotic collection of random bubbles, but an ordered lineage of universes, each giving birth to the next through the natural processes of stellar collapse. The universe itself becomes a living system, one that grows, evolves, and reproduces. But before we dive deeper into what this means for the structure of reality, it's worth stepping back and asking a simpler question. What exactly is a black hole? To understand how our universe could exist inside one, we first need to grasp what these cosmic enigmas truly are, how they form, what makes them so powerful, and why they continue to defy our most fundamental theories of physics. A black hole is one of the most mysterious and extreme objects in the universe, a region where gravity becomes so powerful that nothing, not even light, can escape its grasp. The term black hole might sound poetic, but it perfectly describes its nature. It is both black, because it emits no light, and a hole, because it represents a kind of bottomless pit in the fabric of space-time itself. Yet, unlike an ordinary hole, it isn't a place where matter simply disappears. Rather, it's a region where the rules of the cosmos, as we understand them, stop working. To truly appreciate what it means for our universe to possibly exist inside one, we have to unravel the anatomy of a black hole, from its outer boundary to its terrifying center. Imagine space as a flexible sheet, like a trampoline stretched tight. If you place a small ball, say a marble, on that sheet, it will create a slight dip. This is analogous to how planets and stars curve the fabric of space and time around them. The heavier the object, the deeper the dip. Now imagine placing something so heavy on that sheet that it doesn't just make a dent, it tears right through it, creating a bottomless funnel. That's what a black hole does to spacetime. Its gravity is so overwhelming that space doesn't merely curve around it, it folds in on itself. This immense gravity comes from the collapse of mass into an incredibly small volume. A black hole can form when a massive star, many times heavier than our sun, exhausts its nuclear fuel. Without the outward pressure from fusion to counteract gravity, the star's core collapses under its own weight. If the collapsing mass is large enough, nothing can stop the contraction. The density increases beyond comprehension, and the star's matter is squeezed into an infinitely small point, the singularity. Surrounding that singularity is the event horizon, an invisible boundary marking the edge of no return. Anything that crosses this boundary, light, matter, or even space itself, is irrevocably drawn inward.
The event horizon is not a solid surface. It's more like a one-way door. From the outside, it marks the region beyond which nothing can escape. But from the inside, it's the gateway to a domain where time and space trade places. To an external observer, an object falling toward a black hole seems to slow down as it approaches the event horizon, never quite crossing it. Its light becomes redder and fainter until it fades completely. But to the object itself, time continues normally, and in a fraction of a second, it plunges past the horizon, journeying toward the singularity. From its perspective, there's no pause, no hesitation, just an unstoppable descent into the heart of the gravitational abyss. The singularity itself defies imagination. It is the point where all the mass of the black hole is concentrated into zero volume and infinite density. At this point, gravity is so intense that the known laws of physics break down. Our equations, even Einstein's, can no longer describe what happens there. Space and time lose their meaning. The very framework that supports cause and effect dissolves. It's not just that we don't know what lies beyond the singularity, it's that within our current understanding, it may not even make sense to ask.
To make this concept more tangible, think of a river flowing toward a waterfall. As you drift closer, the current grows stronger. Eventually, you reach a point where no matter how hard you paddle, you can't escape the pool. That's like the event horizon. Once you go over the edge, you're inside the black hole, swept toward the bottom of the waterfall, which represents the singularity. The difference, of course, is that in the case of a black hole, the waterfall isn't a feature of water. It's a feature of space-time itself. The river isn't flowing through space, space is flowing through you. Another way to imagine it is to picture time and space as directions. In our everyday experience, we can move freely in space, forward, backward, left, right, but we can only move one way in time, forward. Inside a black hole, this relationship flips. The direction pointing toward the singularity becomes as inevitable as the flow of time itself. No matter how hard you try to move away from it, you're simply moving forward in a new kind of temporal dimension where the singularity is the future. In other words, falling into a black hole isn't like being pulled by gravity in the usual sense. It's like being carried inexorably toward a moment in time you cannot avoid. Because if a singularity marks the end of one universe's spacetime, could it also mark the birth of another? Could the infinite density at the core of a black hole be the same kind of singularity that once expanded into everything we see around us? If so, then understanding what a black hole is might be the key to understanding where we came from. Every black hole begins its life as something familiar, a star. But not just any star. To give birth to a black hole, a star must be enormous, many times more massive than our own sun. These cosmic giants live fast and die young, burning through their nuclear fuel in just a few million years. At their hearts, nuclear fusion acts as a constant battle against gravity. The heat and pressure generated by fusion push outward, while the star's immense gravity pulls inward. For most of the star's life, these two forces balance each other perfectly. It is a delicate cosmic dance, a sustained equilibrium that allows the star to shine. But every dance must end, and when the nuclear fuel runs out, the balance collapses, literally. As fusion ceases, the outward pressure that once supported the star vanishes. Gravity, relentless and uncompromising, seizes control. The star begins to collapse under its own immense weight. In smaller stars, this collapse might halt before catastrophe, creating white dwarfs or neutron stars, dense remnants held up by quantum forces. But for the truly massive ones, those with a core several times heavier than our sun, no known force can resist the inward pull. The collapse continues unchecked, compressing the star's mass into an ever smaller volume until it becomes a black hole, an object so compact that its escape velocity exceeds the speed of light itself. The moment the collapsing star's radius falls below a critical limit, known as the Schwarzschild radius, it crosses a threshold that defines the event horizon. From that point onward, nothing can escape its gravitational grip.
The outer layers of the star may explode outward in a brilliant supernova, scattering elements like iron, carbon, and oxygen into space, seeding the cosmos with the building blocks of planets and life. But the core, unable to resist gravity, implodes into darkness. In a fraction of a second, space and time twist violently, forming a well so deep that not even light can climb out. What remains is a singularity hidden behind an invisible curtain, a newborn black hole, both a grave and a gateway. To grasp how profound this process is, it helps to think in terms of geometry rather than destruction. In Einstein's general theory of relativity, gravity is not a force in the traditional sense, it is the curvature of space-time caused by mass and energy. A massive star creates a deep valley in the cosmic fabric, like a heavy ball resting on a stretched sheet. When that star collapses, it doesn't merely sink deeper, it punctures the sheet entirely, warping space and time so severely that all paths lead inward. From the outside, we see a region of infinite curvature where space-time folds into itself. From the inside, the concept of where loses all meaning. The direction toward the singularity is not a location, but a destiny. The bending of space and time during a star's collapse is not just theoretical. Astronomers have observed the echoes of this process in the universe. When two massive stars die and form black holes, the violent curvature of space-time ripples outward as gravitational waves, distortions that stretch and squeeze space itself. In 2015, the LIGO Observatory detected these waves directly for the first time, confirming one of Einstein's most daring predictions. Each ripple was the final heartbeat of a pair of collapsing stars merging into a single black hole. Their deaths recorded not in light, but in the trembling fabric of the cosmos.
At the threshold of collapse, time itself behaves in astonishing ways. For an observer watching from afar, the star seems to slow down as it nears the formation of the event horizon. The light from its surface grows redder, weaker, until it fades completely, appearing frozen at the brink of disappearance. But for an observer falling with the collapsing matter, time feels perfectly normal, and the descent toward the singularity is unstoppable. This paradox arises because the curvature of space-time affects not only how matter moves, but how time flows. Near a black hole, gravity becomes so strong that time dilates dramatically. Seconds near the event horizon might correspond to centuries or millennia outside it. In this sense, the creation of a black hole is not just the death of a star. It's the birth of a new region of space-time with its own temporal rhythm. The collapse doesn't just crush matter, it forges a new geometry of existence. Inside, every trajectory, every possible future points toward the singularity. Space falls inward, and time itself becomes the force that drives the collapse. To fall into a black hole is to move inexorably toward tomorrow, a tomorrow that ends at the heart of infinite density. This bending of space and time isn't merely an abstract concept, it has real observable effects on the world around black holes. The gravitational field is so intense that it can warp the path of light, creating gravitational lensing, a phenomenon where light from distant stars and galaxies bends around the black hole, forming eerie halos and multiple images. The black hole acts as a cosmic magnifying glass, distorting the appearance of whatever lies behind it. Astronomers have captured this phenomenon directly, most famously in 2019 when the Event Horizon Telescope revealed the first image of a black hole's shadow in the galaxy M87. The glowing ring we saw wasn't the black hole itself, it was light twisted and stretched by space-time on the edge of oblivion. Even outside the event horizon, the effects of the collapsing star linger. The immense gravity accelerates surrounding gas and dust into swirling disks of plasma that glow fiercely as they spiral inward. These accretion disks can reach temperatures of millions of degrees, emitting powerful X-rays that we can detect from across the universe. The energy released by matter falling toward a black hole is among the most intense in nature, sometimes outshining entire galaxies. And yet, despite all this violence, the black hole remains perfectly silent. It gives nothing away, revealing its presence only through the havoc it wreaks on its surroundings and the strange dance of light around its invisible edge. In a way, the formation of a black hole is the universe's way of folding its own story inward.
The elements forged in the heart of a dying star, the same elements that make up planets, oceans, and living beings, are drawn back into the gravitational abyss that once birthed them. Creation and destruction are entwined in this process. The death of one star scatters the seeds for new worlds, while its collapsed core becomes a portal to a realm beyond our comprehension. And it is within this act of cosmic collapse that the greatest mystery lies. Because if the formation of a black hole bends space and time so severely that they tear, what happens on the other side of that tear? Could the interior of a black hole represent not an end, but a transition, a passage through which a new universe with its own laws of physics might emerge? To approach that question, we must first understand the nature of the boundary that separates the known from the unknowable, the event horizon, the ultimate edge of existence. The event horizon is one of the most profound and haunting concepts in all of physics, the invisible surface surrounding a black hole where the universe itself seems to change its rules. It is not a solid wall or a glowing ring. There is nothing physically tangible about it. Yet, in the language of space-time, it is as real as the ground beneath our feet. It marks the point of no return, the threshold that separates what can exist in our universe from what is forever lost to it. To cross it is to step beyond the boundaries of known reality, into a realm where time and space swap roles and the future leads only one way, inward. The term event horizon is deeply literal. It represents the horizon beyond which events can no longer affect an outside observer. Anything that passes through it, whether a speck of dust, a planet, or a beam of light, is cut off from the rest of the universe. No signal, no cry for help, no particle of information can ever cross back over that boundary. From our perspective, whatever crosses the event horizon simply disappears, its fate sealed by the geometry of space-time. It's not that light or matter stops existing. Rather, the structure of reality has bent in such a way that all possible paths lead inward. Even light, which always moves at the fastest possible speed, finds that every direction forward now points toward the singularity. To visualize this, imagine standing near the edge of a massive waterfall. Far upstream, the river flows gently and you can still paddle against the current. As you drift closer to the edge, the water moves faster and faster, until at a certain point, the current becomes too strong to resist. That critical point, where escape becomes impossible, is like the event horizon. If you cross it, you're swept over the edge. The difference, of course, is that for a black hole, this waterfall isn't made of water, but of space-time itself. The very geometry of the universe is flowing inward faster than light, and once you reach that region, there is no going back.
What makes the event horizon so fascinating is that, from an external point of view, it behaves like a paradox. If you were to watch an object fall toward a black hole, you would see it approach the horizon more and more slowly, never quite crossing it. The light from the falling object would stretch into longer wavelengths, redder and redder, until it fades completely, appearing to freeze just outside the horizon. Time for the infalling object, from your perspective, seems to stop. But for the object itself, nothing unusual happens as it passes the horizon. It continues to fall freely, feeling no sudden change, and within moments, according to its own clock, it reaches the singularity. This strange contradiction arises because time itself is distorted differently for observers inside and outside the gravitational field. This time dilation, the slowing of time near strong gravity, is one of the most mind-bending consequences of general relativity. It means that near the event horizon, the flow of time relative to the rest of the universe slows to a crawl. For something orbiting close to the horizon, a few minutes might correspond to thousands of years in the outside universe. This isn't science fiction. It's a measurable effect of gravity. Astronauts aboard the International Space Station, orbiting Earth where gravity is slightly weaker, experience time just a little faster than we do on the ground. Near a black hole, that difference becomes extreme. The event horizon also defines a strange kind of geometry, one where inside and outside are not separated by distance, but by destiny. If you are outside the event horizon, You can still choose to move away from it. Your future is open. But if you cross that boundary, every possible future leads only toward the singularity. There is no trajectory, no physical law that allows escape. It's not about being trapped in space. It's about being trapped in time. The singularity becomes as inevitable as tomorrow. And yet, despite its reputation as a devourer of everything, the event horizon is not a surface of destruction. If you were to fall through it, you wouldn't be ripped apart immediately. In fact, for a supermassive black hole, one millions or billions of times more massive than our sun, you might not feel anything unusual at the horizon. The gravitational gradient, or tidal force, across your body would be relatively mild at that scale. You drift silently across, with no jolt, no flash, no boundary to mark your crossing. Only as you journey deeper inward would the pole begin to stretch and crush everything into the singularity's core. The event horizon is not the end. It's the beginning of the fall. From a scientific perspective, the event horizon is also where the deepest mysteries of physics converge. It represents a barrier not just for matter and light, but for our understanding itself. The information paradox proposed by Stephen Hawking arises precisely because of the event horizon. When a black hole consumes something, does the information about what fell in vanish forever? According to quantum mechanics, information cannot be destroyed. But according to general relativity, the event horizon hides it completely. This conflict between the two great pillars of physics continues to drive debates and research today, pushing us toward a future theory of quantum gravity that might reconcile them. The event horizon is also the reason why black holes appear as dark silhouettes against the cosmos. When we see a black hole, as in the image of M87's shadow captured by the Event Horizon Telescope, what we are really observing is light from hot gas orbiting just outside the horizon. The light bends around the black hole due to its intense gravity, creating a bright ring surrounding a dark core, the shadow of the event horizon. It is not the black hole itself we see, but its outline, the edge of visibility. That shadow represents the cosmic divide between being and non-being, between what can still interact with the universe and what is forever beyond its reach. And yet, for all its mystery, the event horizon is also a symbol of balance, a perfect equilibrium where space-time stands on the knife's edge between order and chaos. It's a region defined not by what we know, but by what we cannot know. Once something crosses that boundary, it is gone from our universe, and its story continues beyond our comprehension. For the observer outside, the black hole is a monument to loss. But for whatever lies within, it might be the start of an entirely new realm of existence.
If our own universe truly exists within a black hole, then our cosmic boundary, the edge of our observable universe, might play a role similar to an event horizon. From our side, we see space expanding. From the other side, it might appear as matter collapsing inward. The parallel is uncanny, and it brings us closer to the next great enigma, the singularity itself. That point of infinite density where all known laws of physics cease to apply. What lies at the center of a black hole may hold the answer to where our universe began, and perhaps where all universes begin. At the very heart of a black hole lies something so extreme, so beyond the reach of our physical understanding, that even the greatest minds in science are forced to admit defeat: the singularity. It is the ultimate enigma of the cosmos, a point where all the mass of a collapsed star, or perhaps of an entire universe, is compressed into zero volume. Within that infinitesimal point, gravity becomes infinite, space-time curvature becomes infinite, and the laws of physics as we know them simply stop making sense. It is not merely a place of immense gravity, it is a boundary where our descriptions of reality collapse. Everything, from matter and light to time and space, is crushed into a single, dimensionless point. Einstein's general theory of relativity predicts the singularity with perfect mathematical precision. When the equations that describe the warping of space-time by mass are applied to a collapsing star, the result is inevitable. At some point, the curvature of space-time grows without limit.
gravity becomes infinitely strong, and space and time themselves cease to exist as continuous, meaningful quantities. This isn't an optional feature of the theory, it's a direct consequence of Einstein's mathematics. But that mathematical inevitability also exposes the theory's greatest weakness. General relativity, though astonishingly accurate in describing gravity at cosmic scales, cannot handle infinities. When the numbers blow up, the equations break down. The singularity, in this sense, is a warning sign, a flashing signal that says, here, your understanding ends. But what does that actually mean? Does the singularity truly exist as a point of infinite density, or does it simply mark the limit of our knowledge? Many physicists suspect that the singularity is not a real physical entity, but rather an indication that general relativity is incomplete. It's a bit like following a map to the edge of the known world. When the map ends, that doesn't mean reality stops. It just means we need a better map. To fully understand what happens at or beyond the singularity, we would need a theory that unifies general relativity, which governs the cosmic scale, with quantum mechanics, which governs the subatomic scale. This long-sought theory of quantum gravity could reveal that instead of an infinitely dense point, the singularity is something else entirely. Perhaps a region where space and time take on a new, quantum form. Still, within the framework we have, the singularity represents the most violent, mind-bending transformation imaginable. Picture space itself collapsing inward, folding tighter and tighter until all distances shrink to zero. Every particle, every atom, every bit of energy and information that falls in is compressed together. The distinction between here and there vanishes. The flow of time, which we perceive as a smooth progression from past to future, disintegrates. The singularity is not a location within space. It is the end of space. And it is not a moment within time. It is the end of time. To ask what happens inside the singularity is to ask a question that no longer has meaning, because the very concepts of inside, outside, and when have ceased to exist. To make this more intuitive, consider the fate of an astronaut who falls into a black hole. At first, they would experience stronger and stronger tidal forces. The difference in gravity between their feet and their head would stretch them like spaghetti, a process physicists grimly nicknamed spaghettification. As they approach the singularity, these tidal forces grow without bound, tearing apart atoms, then nuclei, and finally the very fabric of space-time itself. Yet, in a sense, nothing ever truly reaches the singularity in the conventional sense, because time itself ceases to flow there. It's as if the universe folds you into a frozen instant, an eternal, inescapable now. The singularity's nature raises one of the deepest questions in modern physics. What happens to the information about everything that falls into it? If matter, energy, and information are all destroyed there, that would violate a key principle of quantum mechanics, that information cannot be lost. Stephen Hawking wrestled with this paradox for decades, proposing that perhaps information isn't destroyed, but somehow encoded in the radiation emitted by black holes as they slowly evaporate. Yet, without a complete understanding of what's truly at the singularity, the mystery remains unresolved. The singularity is the intersection point of two great theories, relativity and quantum mechanics, and it is precisely where they clash. Some physicists believe that a new understanding of space-time might emerge from this conflict. In certain approaches to quantum gravity, such as loop quantum gravity, space and time are not continuous, but made of tiny, discrete loops, the smallest possible units of existence. In such a framework, the collapse of a black hole might not lead to an infinite singularity at all, but to a region of extreme, finite density where quantum effects create a bounce. Instead of ending in destruction, the collapse could rebound, giving birth to a new expansion, a new universe. This possibility directly links the singularity inside a black hole to the Big Bang that began our own cosmos. The death of one world could seed the birth of another. Even without quantum theory, the idea that space and time themselves could end at a singularity is almost impossible to grasp. It forces us to abandon the comforting notion that the universe has a fixed stage on which events unfold. Instead, The stage itself is part of the story, and the singularity is the point where that story stops being told. The geometry of space-time, so elegantly curved and continuous in Einstein's equations, suddenly becomes nonsensical, a tangled knot of infinities. Some physicists describe it as the universe's way of hiding its secrets, a veil drawn over the face of creation and destruction alike.
Yet the singularity is not just a mathematical curiosity. It may be the most fundamental clue we have about the nature of reality. It represents a limit, a boundary where our theories collapse, but also where new physics must emerge. Just as the discovery of atoms shattered the classical view of matter, understanding the singularity could revolutionize our conception of the cosmos. It's possible that space and time, far from being fundamental, are emergent, arising from a deeper, unknown layer of physics that operates beneath the surface of reality. The singularity may be a window into that hidden layer, a place where the building blocks of existence reveal their true form. If this is true, then what we call a singularity might not be a point at all, but a transition, a gateway through which one universe transforms into another. The infinite density predicted by relativity could be replaced by a bridge to a new region of space-time, where the collapse of one world ignites the birth of another. From the outside, this process would appear as the formation of a black hole. From the inside, it would look like a Big Bang. And in that sense, the mystery of the singularity may not just be about how universes die, but how they are born. The connection between black holes and the Big Bang is one of the most astonishing and elegant ideas ever proposed in modern cosmology. It suggests that our universe may not have begun with something emerging from nothing, but rather as the continuation of something that came before. That what we call the Big Bang might in fact be the other side of a black hole singularity. In this picture, the end of one universe becomes the beginning of another. The same forces that crush matter into oblivion in one realm could ignite the creation of space and time in another. This theory challenges the very meaning of beginning and end, painting a picture of reality as an endless cycle of collapse and rebirth. To understand how this could be possible, we need to look again at what the Big Bang really was. Contrary to popular imagination, the Big Bang was not an explosion that happened in space. It was the rapid expansion of space itself. Every point in the universe was once compressed into an incredibly hot, dense state. When cosmologists run the equations of general relativity backward in time, they find that the universe's expansion leads to a singularity, a point of infinite density, just like the one predicted at the center of a black hole. The mathematical resemblance between these two singularities, the one inside a black hole and the one at the beginning of the universe, is uncanny. In both cases, the known laws of physics break down and space and time themselves are twisted beyond recognition. This similarity has led some physicists to wonder whether the Big Bang and a black hole singularity are not just mathematically similar, but physically connected. What if the Big Bang was the white hole counterpart of a black hole, the mirror image that expels matter and energy instead of swallowing it in? A white hole is a theoretical object predicted by Einstein's equations, one that behaves as the reverse of a black hole. Nothing can enter a white hole, and everything inside is expelled outward. While no white holes have ever been observed, their existence fits perfectly into the equations of general relativity if one extends the space-time geometry of a black hole in a certain way. Imagine then that when a black hole forms in one universe, the collapsing matter doesn't simply vanish into a singularity. Instead, it tunnels through a bridge in space-time, a wormhole-like structure, and re-emerges on the other side as a white hole in a newborn universe. From the outside, the parent universe sees only the black hole, an inescapable pit of gravity. But from the inside, observers in the new universe experience a cosmic explosion, their own Big Bang. In this view, every black hole is a potential cosmic womb, giving birth to a universe within. And perhaps our universe was once such a child, born from the death throes of another. This concept is not purely speculative fantasy. It arises naturally from the equations of general relativity when one considers the full structure of a black hole spacetime. In 1935, Einstein and Rosen explored such a possibility when they described what came to be known as the Einstein-Rosen bridge, a theoretical tunnel connecting two regions of spacetime, which we now call a wormhole. Later, physicists like John Wheeler and Kip Thorne expanded on this idea, showing that under certain conditions, a collapsing black hole could indeed lead to a new expanding region, one that might appear as a Big Bang from the inside. But if our universe was born from such a process, it raises a stunning question. What happened to the universe that came before? Somewhere, in a parent cosmos, perhaps unimaginably older than ours, a massive star or perhaps even an entire cluster of matter could have collapsed into a black hole. Within that black hole, space and time folded inward, and beyond the event horizon gave birth to our universe. From the perspective of that parent universe, the black hole is still there, dark, silent, and unchanging. But for us on the inside, billions of years have passed. Our galaxies have formed, our stars have lived and died, and we have evolved to ask the question, where did it all begin?
This idea offers a breathtaking resolution to one of cosmology's deepest mysteries. What caused the Big Bang, and what came before it? If the Big Bang was the bounce or transformation of matter from a previous universe collapsing into a black hole, then the question of before gains a new meaning. There was a before, but it existed in another cosmic domain, separated from ours by the veil of a black hole's event horizon. What we see as an expanding universe might, from that other side, be the continuation of a collapse. The arrow of time, which points inward in a black hole, flips at the singularity and points outward in our universe, its expansion. The end of one timeline becomes the birth of another. There's also a poetic symmetry to this vision. In our universe, black holes represent death, the final fate of massive stars where all matter and information seem to vanish. Yet, on the other side, these same black holes could represent the ultimate act of creation. The universe, in this sense, is self-recycling. It doesn't end with destruction, it transforms. The matter that falls into a black hole in one universe might seed galaxies, stars, and planets in another. The laws of physics could differ slightly from one universe to the next, depending on the conditions at its birth. Over countless generations of universes, natural selection could even favor those that produce more black holes, and therefore more offspring universes. This is sometimes called cosmological natural selection, an idea proposed by physicist Lee Smolin. In this grand evolutionary picture, universes give birth to universes, and the multiverse itself becomes a living, self-sustaining system. Still, this theory remains largely untested. We can't peer into a black hole or look through the Big Bang to see what lies beyond, but some indirect clues might exist. For instance, subtle patterns in the cosmic microwave background, the faint afterglow of the Big Bang, could carry imprints of a previous universe's collapse. If certain asymmetries or temperature anomalies were detected, they might point toward a connection between our cosmos and a pre-existing one. Though speculative, such hints are precisely the kind of fingerprints scientists hope to one day uncover. Perhaps most profound of all is what this idea does to our understanding of beginnings and endings. In everyday life, these are opposites: life and death, dawn and dusk, creation and destruction, but in the cosmic sense, they may be one and the same. The black hole singularity and the Big Bang singularity could be connected, not just by mathematics, but by reality itself. What we perceive as a beginning may always be the end of something else. If this is true, then every black hole we observe, every dark mouth of gravity at the center of every galaxy, could contain its own universe unfolding inside, perhaps governed by its own unique physical laws and constants. And as we gaze out into our night sky, we might, unknowingly, be watching the birthplaces of countless other universes, just as another civilization in another cosmos once watched the collapse that gave rise to ours. The notion that every black hole might give birth to a new universe is one of the most audacious and transformative ideas in theoretical physics. Known as the inside a black hole hypothesis, it takes the connection between black holes and the Big Bang one step further. Instead of imagining our universe as a single instance of cosmic birth, this theory proposes a recursive, ever-branching multiverse. a vast hierarchy of universes each contained within black holes in their parent cosmos. Every black hole could be a cosmic womb hiding an entire universe inside it, with its own space-time, its own matter, and potentially even its own unique set of physical laws. In this framework, the death of a star in one universe is not merely an end, it is the genesis of an entirely new reality. To appreciate the depth of this idea, it helps to visualize a black hole not as a dead end, but as a bridge. From the outside, the black hole behaves exactly as general relativity predicts. Its gravity is overwhelming, its event horizon is impenetrable, and all matter that falls in appears to vanish. But from the interior, some physicists argue, the black hole's singularity does not represent an absolute termination point. Instead, it may act as a seed for a new expanding space-time, a universe that unfurls inside the black hole, independent of its parent universe. In other words, what is the ultimate collapse from one perspective becomes the ultimate expansion from another. The birth and death of universes may be inseparable facets of the same cosmic process. One of the most compelling arguments for this hypothesis comes from the mathematics of general relativity. The equations governing black holes allow for a continuation of space-time beyond the singularity. The singularity doesn't have to be a true termination point. Rather, it could be a transition. In this new region, space-time would expand outward, and matter that fell in could emerge as the building blocks of an entirely new universe. The physics in this child universe might resemble our own, or it might differ in profound ways. The constants of nature, the strength of fundamental forces, even the number of dimensions could be altered depending on the dynamics at the moment of creation. This opens the possibility of a multiverse in which each universe is subtly different from the next. This idea also provides a natural explanation for why the constants of our universe appear so finely tuned for the emergence of galaxies, stars, and life. If universes are born inside black holes, then universes that produce more black holes have more offspring. Over countless generations, universes that are more conducive to black hole formation would dominate the multiverse, not by conscious intent, but by a process analogous to natural selection. Lee Smolin, one of the main proponents of this concept, calls this cosmological natural selection. In this framework, our universe is not a random accident. It is the product of a cosmic evolutionary process, shaped by the physics that favor the proliferation of black holes and therefore of new universes.
The hypothesis also challenges conventional notions of causality and locality. In our everyday experience, cause and effect operate within a single spacetime. But if black holes contain entire universes, then the effects of one universe, the birth of new ones, may occur in realms completely inaccessible to the parent. There is no communication between them, and yet they are connected in a lineage of creation. The event horizon, which to us seems a final barrier, becomes a one-way boundary separating generations of universes. Crossing it might be impossible from the outside, but from the inside, it's the starting line of existence itself. One intriguing aspect of this hypothesis is the potential for universes with radically different physics. While the laws of general relativity govern black holes and their formation, the conditions at the singularity, or at the moment of re-expansion, could slightly alter fundamental constants. A child universe might have different values for the gravitational constant, the speed of light, or the strengths of electromagnetic and nuclear forces. This could lead to a cosmos that behaves very differently from our own, perhaps one where stars burn faster, galaxies form differently, or even life as we know it would be impossible. In this sense, each black hole could be a crucible for diversity on a cosmic scale. Mathematical models suggest that the creation of a universe inside a black hole is not merely speculative. It can be consistent with known physics if we accept certain extensions of general relativity and consider the role of quantum effects. In some models, the singularity is replaced by a bounce, where the inward collapse reverses into an outward expansion. This is analogous to a white hole, the theoretical time reversal of a black hole, which expels matter and energy rather than swallowing it. The child universe grows and inflates from this bounce, and the interior of a black hole is no longer a point of finality, but a cradle for new cosmic evolution. The hypothesis has philosophical implications as well. It reframes our understanding of existence from a linear narrative to a branching tree. Our universe might be a descendant of a black hole in a parent universe, and every black hole we observe could contain a cosmos of its own, giving rise to more universes in turn. The cosmos, in this view, is not static or finite, it is self-replicating, continuously generating new realms of space-time, each with its own history, structure, and potentially even conscious observers. The concept transforms black holes from cosmic destroyers into cosmic creators, redefining death as a precursor to life on an unimaginable scale. Observationally, testing this hypothesis is extraordinarily difficult because no information can escape a black hole's event horizon. Yet it remains compelling because it resolves deep puzzles about the origins of the universe and the fine-tuning of physical constants. It links cosmology with the life cycles of stars, bridging the gap between the death of matter and the birth of universes. While direct evidence may remain out of reach, indirect signatures, such as patterns in the cosmic microwave background, where the statistical distribution of black holes could someday hint at a deeper multiversal structure. Ultimately, the inside a black hole hypothesis invites us to rethink the universe on an unprecedented scale. If true, it suggests that the cosmos is a living, evolving system, capable of reproducing itself across generations. The death of one star, the collapse into a black hole, becomes the genesis of a new realm of space, time, and matter. We are not just inhabitants of a single universe. We may be participants in an endless chain of cosmic creation, where each black hole is a doorway, each singularity a seed, and each universe a chapter in an infinite, unfolding story of existence. If we allow ourselves to take the inside a black hole hypothesis seriously, a mind-bending picture of reality begins to emerge, one that challenges every instinct we have about scale, existence, and what it means to be part of a universe. Picture a universe within a universe. Imagine that the vast expanse of stars, galaxies, and cosmic voids we observe is not the entirety of existence, but the interior of a black hole in a parent universe. From the perspective of that larger cosmos, our universe might appear as a singular point of intense gravity, a black hole, dark and silent, swallowing matter and energy while giving birth to a realm entirely self-contained, unfolding according to its own rules. Now expand this vision further. Within our universe, black holes continue to form, consuming stars and collapsing matter into regions of extreme density. Each of these black holes could in turn be a portal to a separate universe, a child cosmos branching off from ours. In this way, universes reproduce, like cosmic seeds dispersing through the gravitational soil of their parent reality. It is a nested structure, where each universe is both the offspring of something greater and the progenitor of countless others. From this perspective, the cosmos is not a single, isolated expanse, but a multi-layered hierarchy of existence stretching potentially infinitely outward and inward. The analogy of a nested Russian doll captures this beautifully. Imagine opening one doll only to find a smaller, equally complete version inside. Each layer contains all the structures, complexities, and phenomena of the one outside it. On the largest scales, one universe might be just the interior of a gargantuan black hole in a parent universe. On smaller scales, the black holes scattered throughout that universe could each contain an entirely separate reality, complete with its own stars, galaxies, and physical laws. If this model is correct, then the universe we call home is just one layer in an endless stack of cosmic reality.
This vision of nested universes reshapes our understanding of time as well. In our universe, time flows from the Big Bang outward, allowing stars to form, galaxies to evolve, and life to emerge. But within the parent universe, our own Big Bang might have been just the inward collapse of a black hole, a moment of time from another frame of reference. Similarly, time in the child universes within our black holes may unfold independently, governed by the conditions at their respective singularities. The temporal flow in one layer could be entirely decoupled from another, creating a multiverse where timelines are nested, overlapping, yet causally isolated from one another. From a philosophical standpoint, the implications are staggering. We often think of ourselves as inhabiting a singular, isolated universe, the ultimate reality. But if we live inside a black hole, then the universe is both more intimate and more vast than we can comprehend. We are, simultaneously, the children of a parent universe and the potential creators of countless others, through the black holes scattered across our cosmic landscape. Every massive star that collapses, every black hole that forms, might be the seed of a new cosmos somewhere beyond our perception. We are both contained and containing, part of a grand, recursive cycle of birth and death on an unimaginable scale. This model also forces us to reconsider the relationships between universes. In this hierarchy, a parent universe gives rise to offspring, but has no access to the interiors of its children. Similarly, a child universe grows unaware of the parent that birthed it, except perhaps through subtle clues encoded in the fundamental constants of nature. The multiverse becomes a vast, branching tree. Each universe is both a leaf and a trunk, simultaneously ending and beginning, fully realized yet part of something far larger. The concept collapses the distinction between creation and consumption, showing them as inseparable processes in a cosmic chain reaction. The mathematical frameworks supporting this vision are rooted in general relativity and extensions of black hole theory. Einstein's equations allow for the continuation of space-time beyond a black hole singularity, suggesting that each black hole could host a self-contained expanding universe. Quantum theories, though still incomplete, hint at mechanisms for singularities to rebound or quote-unquote bounce, initiating expansion in new dimensions. While we have no direct observational evidence for nested universes, the parallels between black hole physics and the properties of the Big Bang make the idea compelling. The patterns of density, curvature, and expansion observed in our universe could be consistent with it being the interior of a black hole in another cosmos. This recursive structure, universes within universes, also reframes the concept of scale in a profound way. We tend to measure the universe in light years, galaxies, and clusters. But in a multiverse of nested universes, these measures may be relative. Our entire universe could be microscopic from the perspective of a parent universe, and simultaneously, our black holes could harbor universes unimaginably large to those inside them. Scale in this context is no longer absolute. It is layered, nested, and dependent on the perspective of the observer. Such a vision is both humbling and exhilarating. We are part of something far larger than we can directly perceive. Yet our actions, the collapse of stars, the formation of black holes, may ripple into entirely new realities. Each black hole becomes a nexus of creation, a bridge between the end of one cosmic cycle and the beginning of another. If this idea is correct, then the universe is not a static backdrop for existence, but a self-replicating, multi-layered organism, continuously generating new realms, each with its own laws, history, and potential for complexity. The nested universe model also invites us to ponder the ultimate fate of existence. If black holes can generate new universes, then the cosmos may be eternal, with no true beginning or end, only transformations across scales and layers. Death becomes birth, collapse becomes expansion, and the story of the universe becomes a fractal tale of infinite recursion. Our understanding of life, matter, and time is enriched, knowing that we occupy just one chapter in an ongoing narrative that spans universes, each contained within the next, each giving rise to more beyond. In this light, the cosmos is not merely a backdrop for our existence. It is a living structure, a vast, interconnected system of creation and destruction. We are nested within a universe, which may itself be nested within another, and the black holes we observe could be the seeds of countless other worlds. Every glimpse of a black hole, every observation of its effects, may be a peek into the process by which universes are born. The multiverse in this view is not just a theory, it is a framework for understanding reality itself, as an endless hierarchy of universes, each within another, stretching infinitely inward and outward, each universe a mirror and a doorway.
The profound ideas we've been exploring, universes within black holes, nested cosmic hierarchies, and the possibility that the Big Bang itself was born from a singularity, all find their foundation in the revolutionary insights of Albert Einstein. At the heart of this framework is his general theory of relativity, published in 1915, which redefined our understanding of gravity not as a force, but as the curvature of space-time caused by mass and energy. Einstein's equations describe precisely how matter and energy warp the fabric of the cosmos, dictating how objects move, how light bends, and how time itself flows. They are elegant, precise, and unforgiving, and they open the door to the extraordinary possibility that spacetime could continue inside a black hole, giving rise to entirely new realms of existence. Einstein's field equations, the mathematical backbone of general relativity, relate the geometry of spacetime to the distribution of mass and energy within it. They tell us that massive objects curve the surrounding spacetime, and this curvature dictates how matter moves. When applied to ordinary stars and planets, these equations perfectly reproduce the motions we observe. Planets orbit stars, light bends near the sun, and time ticks slightly faster or slower depending on the strength of gravity. But when the equations are applied to an extreme case, the collapse of a massive star into a black hole, the predictions become truly astonishing. The curvature of space-time grows without bound, leading to the formation of a singularity and an event horizon. Yet, here lies the subtlety that makes universes inside black holes conceivable. The equations of general relativity do not strictly prohibit the continuation of spacetime beyond the singularity. They merely predict an infinite curvature if treated in the classical sense. If we allow for extensions, for instance, taking into account quantum effects or treating the singularity as a bridge rather than an endpoint, the equations imply that spacetime could be continuous through this extreme region. In other words, the singularity might not be a dead end, but a doorway. From the perspective of the mathematics, what appears to be a one-way trap from the outside could, from the inside, unfold as a region of expanding spacetime, the beginning of a new universe. The concept can be illustrated by examining the Schwarzschild solution, one of the simplest solutions to Einstein's equations that describes a non-rotating black hole. According to this solution, spacetime outside the event horizon behaves predictably. Objects follow paths determined by gravity, light bends, and orbits are stable at certain distances. However, when the solution is extended inward toward the singularity, the mathematics predicts that radial distances effectively switch roles with time. In this warped geometry, all paths inevitably lead toward the singularity, just as we discussed previously. But the equations also allow for the theoretical continuation of spacetime into a new domain beyond the singularity under the right conditions. This is not a violation of relativity, it is a subtle feature encoded in the equations themselves, waiting for a framework that can fully describe what happens at extreme density and curvature. Rotating black holes, described by the Kerr solution to Einstein's equations, make this possibility even more fascinating. Unlike the simple Schwarzschild black hole, a Kerr black hole possesses angular momentum, causing its interior structure to become far more complex. Instead of a singular point, the mathematics suggests the existence of a ring singularity, a loop of infinite density, and theoretical regions where spacetime could extend through throats or tunnels, potentially connecting to other regions or universes. These solutions imply that the geometry inside a black hole is not necessarily destructive in an absolute sense. Instead, it could provide a passage to a new expanding spacetime beyond the singularity. In this framework, every black hole could be the seed of the universe, a self-contained expansion that obeys its own local physics while remaining mathematically consistent with the parent universe. Einstein's equations also provide a natural mechanism for the apparent self-reproduction of universes. If a collapsing mass forms a black hole and space-time continues inside, then the expansion of the interior universe could mirror the conditions of the Big Bang. The equations that govern the outward expansion in our universe are formally similar to those that describe space-time geometry inside a black hole. This remarkable symmetry has led some physicists to propose that the Big Bang could have been the emergence of a new space-time region inside a parent black hole, connecting the most violent collapse imaginable with the most explosive creation. In this view, the mathematics of general relativity predicts not just the formation of black holes, but potentially the birth of universes. Moreover, General relativity allows for the existence of wormholes, hypothetical structures that act as shortcuts through spacetime. The Einstein-Rosen bridge, an early example of such a concept, describes a tunnel connecting two separate regions of spacetime. While wormholes are often considered unstable or untraversable, the mathematics shows that under certain conditions, space-time can be continuous through extreme curvature, suggesting that what seems like a boundary or an end from one perspective may be the beginning from another. This reinforces the idea that black holes are not just cosmic endpoints, but potential gateways to new regions of reality. It's also worth noting that the ability of general relativity to predict these phenomena does not imply that we can directly observe or traverse them. The theory provides the rules for how space-time behaves, not necessarily for how we experience it from inside a black hole. But the mere fact that Einstein's equations allow for continuous space-time beyond the singularity is profound. It shows that the universe, governed by the same laws of physics we measure in our laboratories and telescopes, might be capable of reproducing itself in ways that challenge our intuition, stretching the imagination from the infinitely small to the infinitely vast. In essence, general relativity provides the scaffolding for a multiverse in which universes emerge from black holes. The equations describe how matter and energy warp space-time, how time and space can exchange roles, and how extreme conditions near a singularity might lead to entirely new expansions. Within this mathematical framework, a black hole is not merely a cosmic grave, it is a locus of potential creation. The interplay between gravity, space-time curvature, and mass energy forms a foundation upon which the idea of nested universes rests. Without Einstein's insights, the inside a black hole hypothesis would have no footing. With them, it becomes not just plausible, but an inevitable possibility within the logic of the cosmos.
The elegance of this perspective is that it unites extremes, the collapse of matter into a singularity and the explosive expansion of a universe are no longer separate events, but two sides of the same equation. Einstein's equations make room for continuity, for the possibility that spacetime does not terminate at a singularity and that the universe is far more dynamic and generative than previously imagined. It is within this framework that we can begin to envision a cosmos in which black holes are not just endpoints, but bridges, linking past and future, death and birth, one universe to another. The deeper we dive into the heart of a black hole, the more apparent it becomes that our understanding of the cosmos is fragmented. On the one hand, we have general relativity, Einstein's majestic theory describing the warping of spacetime, the curvature of gravity, and the macroscopic structure of the universe. On the other hand, we have quantum mechanics, the microscopic framework governing the behavior of particles, energy, and forces at the tiniest scales. Each theory is extraordinarily successful within its own domain, yet when applied to black holes, they collide in ways that reveal profound tensions and unanswered questions. The singularity of a black hole sits precisely at this intersection, a place where the predictions of relativity and quantum mechanics seem to contradict one another, forcing physicists to grapple with a reality that neither theory can fully explain. General relativity treats gravity as a smooth, continuous curvature of spacetime. It predicts that as matter collapses into a black hole, spacetime bends more and more sharply until, at the singularity, it becomes infinite. Quantum mechanics, by contrast, is built upon probabilistic rules and the uncertainty principle. At tiny scales, particles jitter, wave functions fluctuate, and energy cannot be defined with absolute precision. When a collapsing star reaches the extreme densities near a singularity, the smooth continuum of spacetime predicted by relativity encounters the inherently discrete, fluctuating nature of quantum phenomena. The clash is unavoidable. How can space and time be infinitely continuous when quantum mechanics forbids absolute precision in energy, position, and momentum? This conflict becomes particularly acute at the event horizon and singularity. General relativity suggests that information about the matter falling into a black hole is forever trapped behind the event horizon, ultimately being destroyed at the singularity.
Quantum mechanics, however, maintains that information cannot be destroyed. This is the heart of the black hole information paradox, first articulated by Stephen Hawking. If a black hole evaporates through Hawking radiation, a quantum effect whereby particle-antiparticle pairs near the event horizon allow the black hole to lose mass, the information about everything that fell in seems to vanish from our universe. Quantum theory says that is impossible, while relativity's classical predictions suggest it happens unavoidably. The paradox reveals a profound inconsistency between the two pillars of modern physics, highlighting the need for a unified framework to understand the true nature of black holes. Another aspect of this conflict is time and causality. Relativity predicts that time slows dramatically near a black hole's event horizon. To an outside observer, an infalling object appears to freeze at the horizon, while for the object itself, time flows normally until it hits a singularity. Quantum mechanics introduces additional subtleties. Particles do not have fixed trajectories, but exist as probabilities until measured. Reconciling these two pictures, one deterministic and geometric, the other probabilistic and uncertain, is far from trivial. How does a quantum particle behave when the very fabric of spacetime it occupies is being stretched, twisted, and compressed beyond comprehension? The conflict also raises questions about energy and vacuum fluctuations. Quantum mechanics predicts that even empty space is not truly empty, but teems with virtual particles that pop in and out of existence. Near a black hole, these fluctuations can produce observable effects such as Hawking radiation. General relativity, in its classical form, does not account for such quantum vacuum effects. Understanding what actually happens inside a black hole requires a theory that can describe how space-time geometry interacts with these quantum processes, something neither relativity nor quantum mechanics can do alone. Attempts to reconcile these two domains have led to speculative but mathematically rigorous approaches like string theory and loop quantum gravity. String theory posits that the fundamental building blocks of matter are one-dimensional strings whose vibrations create particles. In such a framework, the singularity might be avoided entirely, replaced by a finite extended object, allowing for a continuous connection between a collapsing black hole and the potential birth of a new universe. Loop quantum gravity, on the other hand, envisions spacetime as quantized, a network of discrete loops that replaces the smooth continuum that relativity proposes. In this scenario, the infinite density predicted by relativity at the singularity is avoided, and black holes might bounce, forming new regions of spacetime rather than ending in true infinities. The importance of quantum mechanics in this context cannot be overstated. Without accounting for quantum effects, our description of a black hole is incomplete and, in some respects, physically impossible. Relativity predicts singularities of infinite density, which are unphysical, while quantum mechanics provides mechanisms that could regularize these infinities. At the same time, without relativity, quantum mechanics cannot describe the extreme curvature of spacetime that defines a black hole. The interplay between these theories suggests that the ultimate nature of black holes, and by extension, the possibility of universes inside them, can only be understood through a synthesis of the two, a theory of quantum gravity.
This synthesis is not merely a technical challenge, it is a philosophical and conceptual one. It requires rethinking the very meaning of space, time, and existence at their most extreme. In such a framework, the singularity may not be a point of destruction, but a bridge to new spacetime, with quantum fluctuations seeding the expansion of a new universe. The event horizon might act as a boundary where information is preserved in subtle, non-local ways, reconciling the deterministic structure of general relativity with the probabilistic nature of quantum physics. Together, these theories hint at a universe that is both far stranger and far more beautiful than we can currently imagine. Ultimately, the conflict between quantum mechanics and general relativity is not just a problem to be solved, it is a window into the unknown. It tells us that black holes are more than cosmic curiosities. They are laboratories at the limits of reality, places where the universe pushes its laws to the breaking point. Understanding what lies within them requires going beyond our current physics, uniting the large-scale curvature of spacetime with the jittery, probabilistic microcosm of quantum theory. Until we achieve that union, The interior of a black hole and the possibility that it contains an entire new universe remains one of the most tantalizing mysteries in all of science. One of the most confounding puzzles in modern physics arises precisely from the clash between general relativity and quantum mechanics, the black hole information paradox, famously highlighted by Stephen Hawking in the 1970s. The paradox emerges from a simple but profound question. What happens to the information about the matter and energy that falls into a black hole? In quantum mechanics, information about a system's state, the arrangement of particles, their energy, momentum, spin, and other properties, cannot be destroyed. This is a fundamental principle. If information were lost, the predictability of quantum theory would collapse, and the entire framework of physics would be undermined. Yet, according to classical general relativity, anything that crosses a black hole's event horizon is lost to the outside universe, seemingly disappearing forever, especially as the black hole eventually evaporates through Hawking radiation. Hawking's calculations added a shocking twist to this dilemma. He showed that black holes are not entirely black. Quantum effects near the event horizon allow them to emit radiation. This so-called Hawking radiation slowly leaks mass and energy from the black hole, causing it to shrink over vast timescales. The radiation itself, however, appears completely random, carrying no discernible information about what fell into the black hole. If a black hole can completely evaporate, as these calculations suggest, the information about all the matter it absorbed would seem to vanish permanently from the universe. This violates the core tenets of quantum mechanics and creates an apparent paradox. The laws of the universe appear to be in conflict at a black hole's edge. The implications of the information paradox reach far beyond the fate of particles or atoms. They strike at the very heart of reality and the potential for universes within black holes. If information can truly be destroyed inside a black hole, then the precise arrangement of matter, energy, and possibly even the initial conditions that could give rise to a new universe would be lost. In other words, the very seed from which a child universe might grow could be obliterated. On the other hand, if information is preserved, somehow encoded in subtle correlations in the Hawking radiation or in the structure of space-time itself, then black holes may act not as cosmic graveyards, but as conduits of creation, transmitting the blueprint for a new universe to emerge from the singularity. This paradox has spurred a wide variety of theoretical proposals. One idea is the holographic principle, developed in part by Gerard Thiehooped and Leonard Susskind, which posits that all the information about the matter within a volume of space can be represented on its boundary. In this case, the event horizon of a black hole. According to this principle, the information about everything that falls into a black hole is not destroyed, but is stored in a two-dimensional surface that encodes the three-dimensional interior. In a sense, the event horizon acts as a cosmic hard drive, preserving data that could later be accessed or transmitted through Hawking radiation. If this is correct, then the interior of a black hole could contain all the information necessary to seed a new universe, resolving both the information paradox and providing a mechanism for universes to inherit properties from their parent cosmos. Another proposal is the idea of black hole complementarity. This theory suggests that the information inside a black hole and the information visible to an outside observer are complementary, not contradictory. For someone falling into a black hole, the information travels inward and remains inside, potentially available for the birth of a new universe. For an outside observer, the same information is effectively smeared across the event horizon and eventually emitted via Hawking radiation. In this way, no information is truly lost. It simply has different manifestations depending on the observer's frame of reference. This concept preserves the fundamental laws of quantum mechanics while accommodating the classical predictions of relativity. A more speculative approach involves firewalls, hypothetical energetic barriers at the event horizon that could encode information in a highly scrambled form. While controversial, the firewall hypothesis suggests that the destruction implied by classical relativity might be replaced by a complex, information-rich boundary. If true, then the formation of a new universe inside a black hole would inherit this information, preserving the causal history of its parent cosmos in ways that are encoded in its initial conditions. In other words, the blueprint for a new cosmos could include not just raw matter, but the encoded story of its ancestors.
The information paradox also intersects with the idea of universes within universes in a striking way. If black holes are indeed portals or seeds for new universes, then understanding how information behaves becomes crucial. A child universe could only reflect the properties of its parent if the information is somehow transmitted through the singularity. Hawking himself speculated that a complete theory of quantum gravity might reveal mechanisms by which information is preserved, even in the face of a singularity, reconciling the apparent contradiction between relativity and quantum mechanics. Until such a theory is fully developed, the fate of information, and by extension the fate of potential universes birthed by black holes, remains one of the deepest mysteries in science. The paradox also encourages a profound reconsideration of the nature of reality. If information is never truly lost, then the universe, or multiverse, may be far more interconnected than we can perceive. Every black hole, every collapse of matter into extreme density may contribute to an unbroken chain of causality stretching across universes. In this sense, black holes are not just destructive, they are custodians of information, repositories that preserve the fundamental data necessary for cosmic reproduction. The singularity becomes less a point of annihilation and more a nexus, where the seeds of future realities are conserved, even if inaccessible to observers in the parent universe. Ultimately, the black hole information paradox is a bridge between the known and the unknown, between destruction and creation. It highlights the limits of our understanding, forcing us to confront the tension between the smooth, deterministic geometry of spacetime and the probabilistic, information-preserving world of quantum mechanics. The resolution of this paradox may not only reveal the true nature of black holes, but also illuminate how universes, perhaps including our own, arise, evolve, and are transmitted across the vast nested expanse of the multiverse. In this sense, the information paradox is more than a problem of physics, it is a clue to the profound architecture of reality itself, hinting that death and creation, collapse and expansion, are inseparably entwined at the very heart of existence. If black holes represent the ultimate gravitational traps, devouring everything in their path, then white holes stand as their mirror image, theoretical objects from which nothing can enter, only exit. In the equations of general relativity, white holes emerge naturally as time-reverse solutions of black holes. While black holes pull matter inward across their event horizons, white holes push it outward, expelling energy and matter into space. In a sense, a white hole is a cosmic fountain, spewing forth the contents that have passed through a black hole singularity, potentially providing a mechanism for the birth of a new universe. While no white holes have ever been observed, their existence is consistent with the mathematics of relativity, and they offer an intriguing framework for understanding how a collapsing black hole could lead to a universe like ours. The concept of a white hole becomes particularly compelling when considered alongside the Big Bang. If we imagine that a black hole in a parent universe compresses matter and energy into an extreme singularity, then a white hole could represent the other side of that collapse. The matter and energy would not vanish, but would re-emerge in a new spacetime, expanding outward in all directions, an explosive event indistinguishable from the Big Bang to observers within the new universe. In this model, the birth of a universe is a natural consequence of the death of another, and white holes serve as the bridge connecting the end of one cosmic epoch to the beginning of another. White holes also provide a potential solution to some of the conceptual problems raised by black holes. For instance, the black hole information paradox raises questions about whether information is lost forever. If a black hole leaps to a white hole in a new universe, then the information carried into the black hole could be preserved and released in the offspring universe. In this way, the universe inside a black hole would inherit the physical characteristics, energy distributions, and perhaps even the fundamental constants of the parent universe. White holes thus offer a theoretical pathway for cosmic information to survive and propagate across generations of universes, maintaining a continuity that defies the destructive appearance of black holes from the outside.
The idea of white holes also introduces profound implications for causality and time. A white hole, being a time-reverse black hole, operates in a sense where the temporal arrow appears to be flipped. From the perspective of the parent universe, the black hole draws matter inward in a forward temporal direction. From the perspective of the new universe, the white hole expels that same matter outward in what seems to be an outward expansion, its own flow of time moving away from the singularity. This duality between collapse and expansion hints at a symmetry in the universe's structure. The same event that appears as an endpoint in one frame of reference becomes a beginning in another. In this way, time itself may be locally oriented within each universe, but globally part of a continuous chain of cause and effect spanning nested realities. Mathematically, white holes are intriguing because they allow for solutions to Einstein's equations that are entirely consistent, if exotic. While black holes have event horizons that nothing can escape, white holes have event horizons that nothing can enter. Matter expelled from a white hole would move along geodesics dictated by space-time curvature, inflating the new universe and setting initial conditions that determine the formation of structures like galaxies, stars, and planets. If the singularity of a black hole leads directly into a white hole, the process effectively converts extreme gravitational collapse into expansive creation. In this sense, white holes act as cosmic fountains of matter, energy, and information.
The white hole theory also fits naturally into the broader idea of a multiverse. Every black hole could produce a white hole, giving birth to a new, self-contained universe. The laws of physics in these universes could vary slightly, influenced by the conditions of the parent black hole and the dynamics at the singularity. Over countless generations of universes, a vast and intricate tree of realities could emerge, with black holes serving as wombs and white holes serving as birth canals. Each universe would be both a product of its ancestors and a potential progenitor for countless others. This nested, self-replicating structure redefines our understanding of cosmology, turning the death of matter into a generative force, capable of producing entire realms of existence. Some physicists have speculated that remnants of white holes could exist in our own universe, potentially observable as unusual bursts of energy or matter. For instance, some gamma-ray bursts, intense flashes of high-energy radiation detected from distant parts of space, have been proposed speculatively as candidates for white hole events. While this idea remains highly conjectural, it underscores the possibility that white holes, though elusive, might leave observable fingerprints in the cosmos, hinting at the connection between black holes and the birth of universes. Ultimately, white holes provide a remarkable conceptual bridge. They turn the end of a black hole singularity into a beginning, offering a mechanism by which matter, energy, and information are not destroyed but transformed. If the inside a black hole hypothesis is correct, then each black hole could be linked to a white hole somewhere else, forming a continuous chain of cosmic creation. Our own universe, in this framework, might be the product of a white hole that emerged from a black hole in a parent cosmos. The collapse of one reality, the singularity, becomes the spark of another, and the seemingly destructive power of black holes is revealed as a force of cosmic fertility. The symmetry and elegance of this picture are stunning. Black holes pull inward, white holes push outward. Collapse and expansion are two sides of the same cosmic coin. Matter and energy do not disappear, but are recycled, giving rise to new space, new time, and new possibilities. In this way, white holes may represent more than a theoretical curiosity. They may be the very mechanism by which the universe reproduces itself, creating a cascading hierarchy of universes, each nested within another, each born from the extreme conditions at the core of a black hole. Through this lens, the cosmos becomes an endless self-generating cycle, and the boundaries between death and birth, and then beginning, lose their absolute meaning, replaced by an eternal dance of creation. One of the most striking aspects of the black hole universe connection lies in the unexpected parallels between the mathematics of black hole formation and the mathematics describing the Big Bang. At first glance, these processes seem like opposites. One is the collapse of matter into an infinitely dense singularity. The other is the explosive expansion of space from a similarly dense state. Yet when we examine the underlying equations, rooted in general relativity, a remarkable symmetry emerges. Both scenarios involve extreme curvature of spacetime, singularities where conventional physics breaks down, and solutions that dictate the dynamics of energy, mass, and geometry in the universe. The similarities suggest that collapse and expansion might not be separate phenomena, but rather two manifestations of the same fundamental rules, operating in reverse depending on perspective. Consider the Friedmann equations, which govern the expansion of the universe according to general relativity. These equations relate the rate of expansion, the density of matter and energy, and the curvature of space. When extrapolated backward in time, they predict that the universe was once in an incredibly dense, hot state, a singularity, where the scale factor shrinks to zero and spacetime curvature becomes extreme. Now, compare this with the equations describing a black hole, particularly the Schwarzschild solution for a non-rotating black hole. These describe the collapse of matter under gravity into a singularity where radial distances shrink to zero and curvature diverges. Mathematically, both scenarios involve singular solutions in Einstein's equations. One represents inward contraction, the other outward expansion. The structural symmetry is uncanny. It is almost as if the universe's birth mirrors a death at a smaller scale.
This symmetry extends beyond the abstract mathematics. The density, temperature, and energy scales involved in a collapsing black hole echo the conditions of the early universe. In the moments after the Big Bang, the universe was so hot and dense that conventional matter could not exist. Particles collided at extreme energies, and quantum effects dominated. Inside a black hole singularity, matter is similarly compressed to the point where atomic structure and even subatomic integrity ceases to be meaningful. Both systems operate in a regime where classical physics alone cannot describe reality. The parallel suggests that black holes may indeed be microcosms of the same processes that drove the early universe, only contained and hidden from our observational perspective. Furthermore, the dynamics of space and time show intriguing correspondences. In the universe's early moments, space expanded at an incredible rate, driven by energy density and potentially by inflationary processes. In a black hole, space as we know it is warped inward. But in certain theoretical models, particularly those considering quantum gravity or white hole transitions, the inward collapse can bounce, producing a new spacetime that expands outward, akin to a Big Bang in miniature. In this way, the mathematics does more than suggest symmetry. It offers a mechanism by which the end of one system can seed the beginning of another. The black hole singularity may be the mirror image of our own universe's initial expansion. Even the equations describing energy conservation reveal parallels. In both the Big Bang and black hole scenarios, the gravitational potential energy plays a dominant role, dictating the motion of matter and the curvature of space-time. In a collapsing star, gravitational energy drives the matter inward, accelerating the formation of a singularity. In the expanding universe, the energy density of the primordial plasma drives rapid expansion, creating the large-scale structures we observe today. Both systems involve a transformation of energy from one form to another under extreme curvature conditions, and in both, the distribution of mass and energy determines the geometry of spacetime. The patterns repeat, revealing a kind of cosmic echo between the processes of birth and death. Even the thermodynamics of black holes, encapsulated in Hawking radiation and the concept of black hole entropy, resonates with the universe's initial conditions. The entropy of a black hole is proportional to the area of its event horizon, suggesting a deep link between information, geometry, and energy. Similarly, the early universe can be characterized by its own thermodynamic properties, temperature, density, and the distribution of energy and particles. Both systems are subject to the same fundamental laws, yet they manifest them in reverse. One contracts and hides information behind the horizon, the other expands and distributes it across an inflating cosmos. The similarities hint at a universal principle, where extreme states of matter and energy obey mirrored patterns whether collapsing inward or bursting outward. The notion that collapse and expansion are mathematically dual is further supported by models of quantum cosmology. In some approaches, the equations describing a collapsing black hole can be transformed, through a change in coordinates or through quantum corrections, into equations that describe an expanding universe. The singularity at the center of a black hole can become a bounce point, initiating growth in a new space-time continuum. This formalism strengthens the idea that our own universe could be the interior of a black hole formed in another cosmos. The math does not just allow the idea, it predicts the possibility. On an even deeper level, these similarities suggest that the laws of physics themselves are not arbitrary. The recurrence of the same equations, the same patterns of density, curvature, and energy implies that the processes governing black holes and cosmic expansion are expressions of the same underlying reality. If black holes can give rise to new universes, and if the mathematical structure of general relativity ensures that such processes mirror the Big Bang, then the cosmos may be fundamentally self-replicating. Collapse leads to creation, death to birth, and the patterns of existence repeat across layers of reality in an elegant cosmic recursion. In a sense, the math offers a glimpse of the universe's secret architecture. Singularities and expansions, black holes and big bangs, all governed by the same fundamental equations, revealing a continuity across scales and processes. The universe, whether seen as a collapsing star or an expanding cosmos, appears to obey patterns that echo across generations of space and time. These cosmic similarities are not merely coincidental. They're the fingerprints of a deeper principle, one that ties together creation, destruction, and the endless possibility of universes born within black holes. The idea that our universe might exist inside a black hole, and that every black hole in turn could contain its own universe, is breathtaking in scope. But it faces a crucial challenge. How could we ever test it? After all, by definition, the interior of a black hole is hidden behind the event horizon, sealed off from observation. No light, no signal, no piece of information can escape to tell us what lies within. Yet despite these seemingly unsurmountable barriers, scientists have sought indirect evidence, faint cosmic whispers, subtle imprints in the structure of space-time, and patterns in the cosmic background radiation that might support or at least be consistent with the hypothesis. While we may never peer directly behind an event horizon, the universe itself could carry the echoes of its black hole origins, woven into its geometry and energy distribution. One of the most promising sources of clues lies in the cosmic microwave background, the faint afterglow of the Big Bang. This radiation, discovered in 1965, pervades the universe in every direction, providing a snapshot of the cosmos when it was just 380,000 years old. It is, in a sense, the fossil light of creation. If our universe were born from the singularity of a black hole, then the conditions of that birth, the energy density, curvature, and distribution of fluctuations might reflect properties of the parent universe. Some cosmologists have speculated that certain anomalies in the CMB, such as slight asymmetries or cold spots, could hint at irregularities inherited from the black hole's collapse. While these interpretations remain speculative, they remind us that the CMB is more than a relic of expansion. It may be the imprint of a deeper cosmic ancestry. The curvature of space-time itself offers another potential clue. According to general relativity, the large-scale geometry of the universe, whether it is open, closed, or flat, depends on its total energy density. Observations suggest that our universe is astonishingly close to flat, with only minuscule deviations. This balance between expansion and gravitational curvature is so precise that it has puzzled cosmologists for decades. If our universe were born from the interior of a black hole, this fine-tuning could be a natural consequence of the initial conditions inside the parent black hole. The immense gravitational curvature of the collapsing star could flatten out during the bounce or white hole expansion phase, producing a universe that appears flat to its inhabitants. What seems like a miraculous coincidence in conventional cosmology might instead be a natural byproduct of our cosmic lineage. Gravitational waves, ripples in the fabric of space-time, may also hold clues. These waves, first directly detected in 2015 by the LIGO Observatory, are produced by cataclysmic events such as merging black holes. While the waves we currently detect come from events within our own universe, future observations might reveal patterns or signatures that deviate from expected models. Some researchers propose that if our universe were born from a black hole, subtle distortions or echoes in the gravitational wave background might betray that ancestry. These could manifest as irregularities in frequency, amplitude, or polarization, fingerprints of a cosmic birth rather than a random quantum fluctuation. Additionally, the large-scale structure of the universe, the vast web of galaxies and voids, may encode hints about its origin. If our universe emerged from a black hole, the initial conditions of that process could influence how matter later clustered. Certain statistical patterns in galaxy distributions or dark matter density might deviate from predictions of standard inflationary models, suggesting a non-traditional beginning. Observations of large-scale anisotropies, or regions where the universe expands at slightly different rates, could also point to inherited traits from a rotating or charged black hole. If the parent black hole had angular momentum, its spin might imprint a preferred axis or asymmetry onto its offspring universe, subtly shaping its cosmic geometry. There are even ideas that connect the Planck scale physics of black holes with observable cosmic phenomena. The Planck scale defines the smallest meaningful unit of space and time where quantum gravity effects dominate. If our universe emerged from such a regime, tiny quantum fluctuations could have been stretched by cosmic expansion into the large-scale density variations we observe today. These fluctuations, in turn, seeded the galaxies and cosmic structures that fill the universe. Thus, the very pattern of stars and galaxies might trace back to quantum ripples generated in the birth of our universe, a signature of its black hole origins. Beyond observational astronomy, theoretical consistency provides its own kind of evidence. The black hole origin model elegantly unifies aspects of cosmology and relativity that otherwise seem arbitrary. It explains why the universe appears homogeneous and isotropic, the same in all directions despite its vast size. In the black hole model, this uniformity arises naturally because the interior of a black hole, from the perspective of a new universe, expands rapidly from an initial nearly symmetrical state. The same mechanisms that make the event horizon smooth and spherical could impose large-scale smoothness on the expanding cosmos. In this way, the model not only fits existing observations, but does so without invoking additional speculative elements. Nevertheless, there are limits to what we can test. The event horizon remains an unyielding barrier. Even if another universe lies beyond it, no signal from that realm can ever reach us. This doesn't mean the hypothesis is unfalsifiable, just that the evidence must be sought in indirect or statistical ways. We may never see into another universe, but we can look for the fingerprints of such an origin imprinted in the cosmic background, in the distribution of matter, or in the subtle behavior of space-time itself. Future technologies may bring us closer to answers. As instruments like the James Webb Telescope, next-generation gravitational wave detectors, and cosmic background observatories refine our view of the universe, they may detect subtle patterns or discrepancies that hint at something more profound, something beyond the standard cosmological model. Perhaps we will find irregularities that defy the inflationary paradigm, or signatures that point to inherited rotation, curvature, or quantum fluctuations from a prior reality. Each new observation gives us another chance to glimpse the shadow of our cosmic origin.
In the end, the search for observable clues is not just about verifying a hypothesis, it is about deepening our understanding of what the universe is and where it comes from. The idea that our cosmos was born from a black hole in another universe transforms the way we interpret the data we already have. The faint hiss of the cosmic background, the stretching of space-time by gravitational waves, the distribution of galaxies across billions of light years, all may be parts of a larger story, a narrative in which our universe is both the child of another and the parent of many more to come. The evidence may be subtle, scattered across the cosmos like the remnants of a forgotten message, but it invites us to look deeper, to listen more carefully, and to question whether the universe we see is merely one verse in an infinite cosmic poem. Despite all the elegant mathematics, tantalizing hypotheses, and indirect evidence we can muster, There is a hard limit to what we can truly know about black holes. We cannot directly observe what lies beyond the event horizon. This barrier is absolute. By definition, not even light can escape, which means no telescope, no gravitational wave detector, and no conceivable probe can ever send back information from the interior. All the theories about universes within black holes, white holes, or singularities remain, at their core, speculative, because they venture into realms permanently hidden from direct observation. While this limitation is frustrating, it also heightens the fascination, challenging physicists to reason, infer, and model reality in ways that stretch both imagination and mathematics. The limitation of our knowledge is not just practical, it is fundamental. Classical general relativity predicts that once something crosses the event horizon, it is irretrievably lost to our universe. Quantum mechanics complicates the picture by insisting that information cannot be destroyed. But even here, any solution remains hypothetical because we cannot measure the outcomes inside the black hole. The tension between what we can know and what we can mathematically describe sits at the heart of modern theoretical physics. We are forced to rely on indirect clues: the radiation emitted at the black hole's edge, the gravitational interactions it imposes on nearby objects, or patterns in cosmic structures that might hint at a deeper origin. These traces allow us to infer possibilities, but certainty is forever out of reach. This fundamental inaccessibility imbues black holes with a sense of mystery that is almost philosophical. They are not merely extreme objects of physics. They represent the ultimate boundary of human knowledge, a region where even our most successful theories, relativity and quantum mechanics, struggle to converge. The singularity, the event horizon, and the potential inside all exist in a realm beyond empirical verification. Yet paradoxically, this very inaccessibility may be what allows black holes to serve as potential incubators of new universes. If no information can escape, the interior might evolve according to its own rules, unconstrained by the observational reality of the parent universe, allowing for a cosmos entirely separate from ours. At the same time, the limits of our knowledge do not mean the ideas are worthless. They are a testament to human ingenuity. Physicists have developed remarkable theoretical frameworks that explore possibilities without direct measurement. The predictions of Hawking radiation, the concept of white holes, the inside a black hole hypothesis, and multiverse theories all emerge from the careful extrapolation of known physics into the inaccessible. These ideas are self-consistent within their mathematical frameworks, providing glimpses of what might exist beyond the veil. The very act of contemplating what cannot be seen pushes the boundaries of understanding, blending physics, mathematics, and philosophy in ways few other problems in science do. The speculative nature of these ideas also invites humility. Unlike most areas of experimental science where observation can confirm or falsify a theory, the interior of a black hole forces us to operate with abstraction, thought experiments, and indirect reasoning. Yet history shows that such speculation can be powerful. The prediction of black holes themselves, long before observational evidence, illustrates that rigorous theoretical reasoning can precede empirical confirmation. It is entirely possible that our current models of universes inside black holes are early glimpses of a truth that may one day be supported by subtler, indirect evidence, or refined by a future theory of quantum mechanics that unites relativity and quantum mechanics.
Ultimately, the limits of our knowledge serve as both a boundary and a frontier. They remind us that black holes are not just extreme objects of physics, but profound mysteries at the edge of comprehension. We cannot look inside, yet we can reason, imagine, and extrapolate with extraordinary precision. The mystery is part of the allure. Each black hole is a closed book, but one whose pages may hold a story of cosmic creation. While we cannot read it directly, the equations, the observations at the edge, and the echoes in the cosmic background allow us to infer, to wonder, and to probe the possibility that reality is far stranger than it appears. In this way, the limits of knowledge do not diminish the hypothesis of universes inside black holes, they enhance it. They make it a question not just of physics, but of imagination, philosophy, and mathematical insight.
We are explorers at the boundaries of reality, and black holes are the ultimate uncharted territories, where speculation and reasoning become our only tools. The truth may be forever out of reach, but the journey toward understanding, tracing the connections between collapse, singularity, and expansion, reveals the remarkable ingenuity of human curiosity. These limits are not failures, they are invitations, challenges to think beyond the observable, and to imagine a cosmos infinitely more complex and beautiful than the one we see. If we entertain the notion that our universe exists within a black hole, the implications extend far beyond physics and mathematics. They plunge deeply into philosophy, reshaping our very conception of reality, origin, and destiny. The first, almost immediate consequence is a radical redefinition of scale. The universe we perceive, all of space, time, and matter, might be the interior of a single point in a parent cosmos. Galaxies, clusters, and superclusters that seem vast from our perspective could be minuscule from the vantage of a larger universe. And the black holes we observe might themselves be cradles for entirely separate universes. Scale becomes relative in a profoundly literal sense, revealing a cosmic hierarchy that dwarfs our ordinary understanding, with layers of existence nested infinitely or perhaps to some unimaginable limit. Origin takes on a new meaning in this framework. The Big Bang, often described as the beginning of everything, would no longer be the absolute origin of existence, but the birth of one universe from the singularity of a parent black hole. The violent high-energy expansion that shaped our cosmos could be seen as a result of processes occurring in a universe that predated our own, suggesting a lineage of universes stretching backward in time. In this light, the universe is not an isolated creation, but a chapter in an ongoing, potentially eternal chain of cosmic evolution. The question of why does anything exist shifts from a metaphysical puzzle to a question of ancestry, continuity, and transformation. Existence begets existence, each universe arising from the collapse of matter and the singularities of the last. Destiny, too, is profoundly affected. If our universe resides inside a black hole, then the formation of black holes within our own cosmos may sow the seeds of countless other universes. The fate of stars collapsing into singularities is no longer merely an endpoint. It becomes a generative act, a mechanism of cosmic reproduction. Each black hole is a potential womb, and the structures we see in our universe, galaxies, massive stars, dense cores, may play a role in a grand, self-replicating process that spans multiverses. In this context, death and destruction are inseparable from creation. The collapse of matter is simultaneously the spark of new reality. Destiny is no longer linear. It becomes recursive, a tapestry of universes nested within universes, each giving rise to the next. Philosophically, the notion that we exist inside a black hole challenges the anthropocentric lens through which we often view the cosmos. Humanity has long assumed that the universe is the ultimate arena of existence, the entirety of reality. If our universe is merely a subdomain of a parent universe and black holes act as portals to new universes, then our understanding of uniqueness and centrality is shattered. We become participants in a cosmic ecosystem, one in which birth, evolution, and death operate on scales far beyond our perception. Our universe, magnificent though it may seem, could be just one of countless others, each with its own history, physical laws, and trajectories. This perspective fosters both humility and awe, situating human existence within an intricate, multi-layered hierarchy. The philosophical implications also extend to the nature of causality and free will. If our universe inherits conditions from a parent black hole, then aspects of our reality, from fundamental constants to the distribution of matter, may be predetermined by processes in another universe. Yet within our own universe, physics allows for complexity, chaos, and self-organization, suggesting that freedom and creativity operate locally, even in a globally constrained framework. The interplay of determinism and autonomy becomes a central theme,
Universes may be born from the laws of their ancestors, yet evolve independently, generating new patterns, structures, and possibilities. In this sense, the multiverse resembles a cosmic symphony, with each universe playing its own theme while contributing to a larger composition. The nested universe hypothesis also reshapes our conception of time. If our universe emerged from a black hole, the temporal sequence we experience is local rather than absolute. The Big Bang becomes not the beginning of all time, but the start of time within our domain. The parent universe, the processes that led to the black hole's formation, and the potential child universes that may emerge from our own black holes exist in a temporal framework that is external and largely inaccessible to us. Time is thus layered, relative, and potentially recursive, challenging our intuition and inviting a broader understanding of causality that stretches across generations of universes. Even questions of meaning and purpose take on a new light. If black holes are the engines of universe formation, then destruction and creation are intertwined in a fundamental cycle. The universe's seemingly random or chaotic events, supernova, gravitational collapses, and the formation of singularities could be seen as essential acts of cosmic fecundity. Life, intelligence, and observation may emerge as natural consequences of this process, part of the universe's unfolding complexity, rather than as accidental or isolated phenomena. In this view, existence is not a mere happenstance, but part of a larger recursive tapestry, where creation is inseparable from destruction, and the universe's evolution is a generative process embedded in the grand architecture of reality. Finally, the psychological and existential impact of this idea is profound. The thought that we live inside a black hole, that our entire universe is a subdomain of something larger, and that our own black holes may give rise to other realities, expands our perspective beyond the familiar scale of space, time, and human experience. It inspires wonder, humility, and a sense of participation in a cosmic process that is both immense and intimate. We are simultaneously contained and containing, observers of a universe that may itself be a single point in a far grander reality, connected to the birth and death of countless other realms. Such a realization transforms not just how we understand the cosmos, but how we perceive our place within it, as both children of a universe and potential progenitors of countless others. In sum, the philosophical implications of living inside a black hole are staggering. They challenge our assumptions about scale, origin, destiny, and meaning, reframing existence as a nested, recursive process. Birth and death, creation and destruction, local freedom and cosmic determinism are woven together in a tapestry that stretches across universes. The universe we inhabit is not an isolated arena, but part of an eternal, self-replicating chain, where every collapse can give rise to a new beginning, and every beginning carries echoes of a prior cosmos. To grasp even a fraction of this perspective is to expand the mind and the imagination, confronting the grandeur and mystery of a cosmos far larger, deeper, and stranger than our everyday experience can convey. The hypothesis that our universe could exist inside a black hole has ignited considerable debate among physicists, highlighting the tension between mathematical elegance and empirical testability. On one side, a number of theoretical physicists find it compelling because it provides a unifying framework for several otherwise disconnected phenomena. They point to the striking similarities between the equations governing black hole interiors and those describing the Big Bang, as well as the conceptual symmetry between collapse and expansion. From this perspective, the hypothesis is not merely imaginative. It is grounded in the very mathematics of general relativity, and when supplemented with quantum considerations, offers a coherent picture in which black holes act as cosmic incubators for new universes. Supporters argue that this framework could explain features of our universe, such as its flatness, homogeneity, and large-scale structure, without relying on additional assumptions like inflation or exotic fields. For them, the idea is a natural extension of known physics, a bold yet mathematically consistent vision of a nested, self-replicating multiverse.
Moreover, proponents emphasize the potential explanatory power of the hypothesis. If every black hole spawns a new universe, it provides a mechanism for the apparent fine-tuning of physical constants. In this view, universes that form in black holes with particular properties are more likely to produce offspring universes with stable physical laws, conducive to complexity, galaxies, and life. This cosmic natural selection model, sometimes called Smolin's fecund universes hypothesis, suggests a universe-generating process that is both testable in principle, through statistical reasoning about observed constants and black hole abundance, and deeply explanatory. The elegance and generative potential of the model appeal to theorists seeking a framework that reconciles quantum gravity, general relativity, and cosmology in a single narrative. On the other hand, skeptics raise serious concerns about the testability and physical reality of the hypothesis. A central critique is that while the equations of general relativity allow for the continuation of space-time beyond a singularity, we have no empirical way to probe such interiors. The event horizon is an absolute boundary. No light or information can escape. As a result, any speculation about universes inside black holes is, for now, beyond observational verification. Critics argue that while the math is internally consistent, it risks becoming metaphysics rather than physics. Without experimental evidence or measurable predictions, it cannot be falsified, which many physicists see as a fundamental criterion for a scientific theory. In this sense, the black hole universe hypothesis occupies a gray zone between rigorous science and speculative cosmology, challenging our definitions of what it means to know the universe. Interestingly, even among skeptics, the hypothesis is taken seriously enough to inspire research. Thought experiments, computer simulations, and theoretical modeling continue to explore the mathematical structure of black hole interiors, the dynamics of singularities, and the potential connection to cosmological expansion. These investigations, though indirect, have generated insights into quantum gravity, black hole thermodynamics, and the relationship between information and spacetime. In other words, even if the idea of universes inside black holes cannot yet be confirmed, it pushes the boundaries of theoretical physics, prompting new approaches to long-standing problems like the black hole information paradox and the reconciliation of quantum mechanics with general relativity.
Some middle ground perspectives acknowledge the elegance of the theory while maintaining a healthy skepticism. These physicists propose that while we may not be able to observe black hole interiors directly, indirect signatures, such as anomalies in the cosmic microwave background, large-scale space-time curvature patterns, or statistical properties of fundamental constants, might someday provide evidence consistent with the hypothesis. In this framework, the idea is treated as a research program rather than a settled explanation. It guides exploration and suggests possible mechanisms without claiming certainty. This balanced approach allows the scientific community to leverage the conceptual richness of the hypothesis while remaining firmly rooted in empirical methodology. Ultimately, the debate underscores a broader truth about theoretical physics at the limits of knowledge. The universe may be far stranger than our instruments can currently reveal, and yet, the imagination, guided by mathematics and logic, remains one of our most powerful tools for exploration. The hypothesis that our universe resides inside a black hole is as contentious as it is compelling. For some, it offers a unifying, generative model of cosmic evolution. For others, it is an elegant mathematical fantasy that may never be tested. Either way, it has reshaped the conversation about black holes, singularities, and the potential for universes within universes, highlighting the profound interplay between imagination, mathematics, and empirical science in the quest to understand reality. The quest to understand whether our universe could exist inside a black hole hinges on the development of both theoretical and observational advances. At present, the interior of a black hole remains hidden beyond the event horizon, inaccessible to any direct measurement, which places immense importance on indirect methods and conceptual breakthroughs. One of the most critical frontiers is the formulation of a complete theory of quantum gravity. a framework that successfully unifies general relativity, which governs the macroscopic curvature of spacetime, with quantum mechanics, which dominates the microscopic realm. Such a theory could illuminate what happens at singularities, clarify how information is preserved or transmitted, and potentially reveal mechanisms by which black holes might give rise to new universes. Without this unification, much of the speculation remains mathematically elegant but physically incomplete. Several approaches to quantum gravity are already under development and offer pathways toward understanding the inside of black holes. String theory, for instance, replaces point-like particles with one-dimensional strings whose vibrations define particle properties. In this framework, singularities might be resolved into finite extended structures, preventing the infinities that classical general relativity predicts. This could allow spacetime to continue smoothly inside a black hole, making it conceivable for a new universe to emerge. Loop quantum gravity, on the other hand, proposes that spacetime itself is quantized, a network of discrete loops that prevent singularities from forming. These loops could generate a bounce at the core of a black hole, producing expansion rather than destruction. Each of these frameworks, while still under development, offer theoretical tools to model black holes as potential cosmic progenitors rather than final graves of matter. Observationally, advances in astronomy and astrophysics may also provide subtle hints about the plausibility of the hypothesis. High-precision measurements of gravitational waves, for example, could reveal deviations from classical predictions that hint at quantum effects near the event horizon. Instruments like LIGO, Virgo, COGRA, and next-generation observatories promise increasingly detailed data on black hole mergers, allowing physicists to test whether the dynamics of extreme gravity align with expectations from general relativity, or whether anomalies might suggest deeper phenomena at work. Even slight discrepancies in waveform patterns could offer indirect evidence of quantum gravitational processes that hint at universes nested within black holes. Similarly, telescopes designed to probe the electromagnetic signatures of black holes, such as the Event Horizon Telescope, EHT, provide unprecedented views of event horizons themselves. Images of the supermassive black hole at the center of M87 and Sagittarius A have already transformed our understanding of black hole environments. Future improvements in resolution, multi-wavelength observation, and time-domain imaging could reveal subtle fluctuations in radiation patterns that encode information about the extreme physics near horizons. Though we cannot peer beyond the event horizon directly, the behavior of surrounding matter, radiation, and magnetic fields may offer indirect clues about the processes occurring inside. Cosmology itself offers another indirect avenue for exploration. The cosmic microwave background, CMB, remains the most detailed fossil record of the universe's earliest moments. Advanced satellite missions, such as the upcoming CMB-S4 project, will map the microwave sky with greater precision, potentially uncovering tiny asymmetries, temperature fluctuations, or polarization patterns that could hint at the initial conditions expected from a universe birthed inside a black hole. Similarly, surveys of large-scale structure, the distribution of galaxies and cosmic voids, could reveal statistical patterns reflecting unusual initial states. While these measurements cannot directly confirm a black hole origin, they may provide circumstantial evidence consistent with the theory. Another promising area involves the study of high-energy cosmic phenomena that might be remnants of extreme black hole physics. Gamma-ray bursts, ultra-high-energy cosmic rays, or unusual gravitational lensing events could in principle carry signatures of physics at energy scales approaching the Planck limit, where the transition between classical and quantum spacetime occurs. If such observations reveal unexpected correlations or extreme events that defy standard models, they may hint at processes relevant to universe formation within black holes. Advanced detectors and space observatories capable of capturing these phenomena could open a window into otherwise inaccessible physics.
theoretical research will also continue to play a crucial role. Physicists are developing increasingly sophisticated computer simulations that model the collapse of massive stars, the formation of black holes, and the behavior of matter and space-time under extreme conditions. These simulations incorporate relativistic gravity, magnetohydrodynamics, and in some cases, quantum corrections. By exploring the dynamics of matter falling into a singularity, researchers can investigate the plausibility of scenarios in which black holes spawn new regions of spacetime. Even if simulations remain idealized, they provide insights into how such processes could occur and what observable consequences might arise. Additionally, interdisciplinary research bridging cosmology, information theory, and thermodynamics could illuminate the behavior of black holes as information-preserving entities. Theoretical work inspired by the black hole information paradox, the holographic principle, and black hole thermodynamics offer avenues for understanding how data about matter falling into a black hole might be transmitted to a new universe. If such mechanisms exist, they could provide testable predictions about correlations in cosmic structures, particle physics, or gravitational phenomena in the parent universe. Each insight from these domains strengthens the conceptual framework for thinking about universes inside black holes, even before direct observational evidence is possible.
Finally, future breakthroughs may emerge from entirely unexpected directions. Historically, many paradigm shifts in physics, from quantum mechanics to general relativity itself, arose from questions that initially seemed unanswerable. The hypothesis of universes inside black holes is similarly situated at the frontier. It is speculative, mathematically rich, and currently beyond direct empirical testing. Yet it has already inspired new theories, new models, and new experiments that push the boundaries of human knowledge. As our theoretical understanding deepens and observational techniques improve, the possibility of finding indirect or circumstantial evidence grows, bringing what was once pure speculation closer to scientific evaluation. In essence, the future of this research depends on a combination of theoretical boldness and observational ingenuity. Quantum gravity, advanced simulations, gravitational wave astronomy, high-resolution black hole imaging, and precise cosmological measurements all contribute pieces of a puzzle that spans scales from the Planck length to the observable universe. Even if we never directly observe another universe inside a black hole, these approaches may reveal whether the concept is physically plausible, consistent with known laws, and capable of explaining features of our cosmos. The pursuit itself, bridging the visible and the inaccessible, the macroscopic and the quantum, is a testament to humanity's drive to understand the deepest mysteries of existence, where black holes are not merely cosmic curiosities, but potential windows into the origins of reality itself. Standing at the edge of this cosmic inquiry, it is impossible to feel a profound sense of wonder. The idea that our universe may reside inside a black hole challenges the very foundations of perception, scale, and existence. Every galaxy, every star, every particle that fills the vast expanse of the cosmos could be part of an interior realm, a reality nested within a point of infinite density in a larger universe. The black holes we observe, enigmatic, destructive, and powerful, could simultaneously be the wombs of entirely new universes, each with its own laws, constants, and history. In this vision, creation and destruction are inseparably intertwined. Death becomes genesis, collapse becomes expansion, and the universe is no longer a singular entity, but a node in an infinite self-replicating cosmic network. The mind reels when we try to imagine the implications. Every black hole in our universe may hide a universe of its own, and within those universes, countless black holes may harbor yet more realities. The process could repeat endlessly, creating layers upon layers of existence that stretch infinitely both downward into parent realms and outward into progeny. Each universe, from the perspective of its inhabitants, would feel like the entirety of reality, yet it could be a mere fragment of a larger, more complex structure. Such a perspective reshapes everything we know about scale, hierarchy, and the very nature of existence. It suggests that the cosmos is not a static expanse, but a dynamic, fractal-like ecosystem of creation, growth, and transformation, where each collapse and expansion is part of a larger, ongoing story.
This view also transforms our understanding of time. If our universe emerged from a black hole, then the flow of time we experience is local, bounded within the interior of our universe. Outside, in the parent cosmos, time may behave differently, and the evolution of other universes may proceed along their own temporal axes. Time becomes a relative, layered phenomenon, each universe experiencing its own chronology, yet all connected through the underlying physics of black holes and singularities. In such a cosmos, past and future, birth and death, beginning and end are no longer absolute concepts. They are points in a vast, interconnected network of creation, where the story of existence unfolds recursively across generations of universes. Equally astonishing is the philosophical implication that our universe, with all its complexity, beauty, and life, may be just one iteration in a grand cosmic lineage. Humanity, in this framework, is both observer and participant in a vast process of universal evolution. The black holes we study, the stars we map, and the cosmic structures we chart could all be intimately connected to a larger narrative of birth, growth, and reproduction of universes. This perspective inspires both humility and awe. We are part of a cosmos far more intricate and profound than everyday experience suggests. Yet, our curiosity and intellect allow us to glimpse the outlines of these hidden processes.
As we reflect on the possibilities, it becomes clear that the pursuit of knowledge is as much about imagination as it is about observation. We may never directly access the interior of a black hole or step into the universe beyond our own singularity. Yet mathematics, theories, and indirect observation allow us to peer across the veil. Every equation, every model, and every photon captured by telescopes may carry whispers of a deeper reality, a story that spans beyond the limits of our observable universe. The search itself, driven by wonder, curiosity, and the desire to understand our cosmic origins, becomes part of the adventure as we confront questions that border on the sublime. Ultimately, if our universe is a black hole, then the cosmos is far larger, stranger, and more interconnected than we can fully grasp. Every black hole we see could be another universe waiting to be born. Each singularity, a potential genesis. Each horizon, a threshold into a hidden realm. The idea invites us to contemplate a universe without boundaries, a reality of infinite recursion, where existence is perpetually created, destroyed, and reborn. It raises a question that is as humbling as it is exhilarating. How deep does the cosmic nesting really go? Each possibility expands our sense of wonder, reminding us that the universe, or the multiverse, is a grand, ongoing story, far beyond our comprehension, yet intimately linked to the very laws that allow us to ask these questions in the first place. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.